for kickstarting the event with your motivating words and sowing seeds of knowledge plan for each one of us. So let's compete and see how tall we can grow our this knowledge plan in this span of 2 days. Without a further minute, let's proceed. You all must already be knowing about our very known first speaker, or you must have googled about him. But if you have not, तो अब कर लेते हैं. He completed his PhD from IIT Bombay under supervision of Professor Sundar Vishwanathan in 2015 and held position of research scientist at Amazon India for an year. He has double postdoctoral degrees in his quiver, one from School of Computer Science, Tel Aviv University, Israel, and the latter from School of Computer and Communication Sciences, EPFL. Now he is Pankaj Gupta Faculty Fellow and Assistant Professor in the Department of Computer Science and Engineering at Indian Institute of Technology, that is IIT Delhi, since 2019. But person's interest better introduce the person. So he loves hiking, running, playing chess, bridge, and has interest in Indian classical music. Algorithm design and analysis, particularly for online and stochastic problems, are his areas of research interest. Research Symposium is being held in IITB, so a student has to travel here if he or she is not here, right? Like you all came here. Assuming all of you are identical,
This is for camera.
you have
This
to
is for
travel
camera.
here
Oh,
to
okay.
attend
Oh,
it.
so
Now
you have
suppose
to use
another event
what
is
for the
planned,
audience says.
then
You have to use
server
two
has to
mics.
travel there,
Sorry, you
right?
have to
Like
use
if
two
we have
mics. Okay, fine,
successful
no
event
problem.
at some other institute, you all will have to go there. So this is the problem, and
So
to
this is working.
optimize the total movement of you all, these servers, this is somewhat like a server problem. I don't know how much I am justifying with the topic about with the speaker, but I will give you a rough idea. Now the density of problem deepens if you all are not assumed to be identical. Each of you has your own personal and other commitments which you have kept aside, and you are here, right, attending this. So that is the associated cost and weight with each server. So that has to be taken care. This is somewhat like weighted case server problem. So this was a simple but not completely matching analogy. So I take this opportunity on behalf of each one in this room to invite Professor Ashish Chiplunkar to enrich our knowledge. The title, The Curious Case of the Weighted Case Server Problem. Please give a huge round of applause. And let's wait, have this curious case as curiosity only till he makes it right.
Thanks a lot for the kind introduction, and a big thanks to CSE IITB for giving me this opportunity to interact with you all. So I was introduced as an assistant professor in IIT Delhi, and as an assistant professor, I like to conduct exams. So here is a surprise quiz for you. Okay, so I will be running a specific algorithm. Okay, so background check. Everybody is a computer science student, right? Raise your hand if you are not a computer science student. Okay, a few of you. Okay, fine. And I suppose at least in the third year? Okay, good, good. So, okay, so you should be able to answer this question then. Cool, so let me run that algorithm. I've just coded it up. Okay, so what is it doing? It's giving me some set and it's asking me for some kind of request. So let me request it something. Okay, it says a miss and it replaces something in that set by the request. Fine. Let me try something else. Oh, it's a hit now. Okay, 4, 5. Let me try a 1 once again. Okay, it says a miss. 1 is back. Any guess what is happening? Okay, somebody said it. Can we pass on the microphone in the audience if possible? Or maybe you'll have to shout. I couldn't figure out who said it, but raise your hand and shout out the answer. Somebody said it. Huh, yeah, go on. Page replacement. What specific algorithm am I using? LRU. Okay, you figured that out. Awesome. Awesome, good. Okay, so yes, I was running the LRU, least recently used page replacement policy essentially. What is the context? When do we at all use this kind of an algorithm? Maybe you could tell? This is the setup, right? So let's work at a very abstract level. Let's say you have a processor, it's giving out read and write requests onto the memory, but that is possible if only if the location at which the read or write has to be performed, that page is in your cache. Okay? So let's say the processor gives a request to page 1. Well, 1 is already in the cache, so that's good. That's called a cache hit. And if the processor gives a request to some page which is not in the cache, it's called a cache miss. And in this case, we need to throw away some page out of the cache and bring in the requested page. Okay? So this takes up some time. Okay? So this takes up a non-trivial amount of delay, and therefore this is counted as 1 unit of cost in the problem that we are going to discuss. So what is the goal? Well, the goal is to design a page replacement policy, a policy which will tell you for every miss, the policy should tell you which page to replace in the cache, and we want it in such a way that it minimizes the number of page replacements over a given sequence of requests. Okay? I hope all of you have seen this problem. Is there anybody who has not seen this? Okay, okay, okay. But is the problem clear to you now? Okay, cool. So now, question number 2 of the quiz, how do we minimize page replacements? What policy should we use to minimize the number of page replacements? No, let's say all that is fixed. Let's say you just have exactly k pages in your cache, that is not in your hand. What is in your hand is what page you replace for every fault. No, not necessarily. That is not necessarily the best policy. Maybe one more trial. The person behind, yeah.
So
good.
The page which will not be used in the future for the longest time.
Longest time. That is what you should throw out. Okay, good. Yes. So he said it. Yes. So the following policy guarantees that the number of page replacements are minimized no matter what the input is. Okay. So it's called the farthest in future FIF policy. What does it say? Okay, when you have a page miss, look for the page which will not be needed for the most amount of time in future and replace it. Okay. Fine. So yes, so that is guaranteed to minimize the number of page replacements on any given sequence of requests. The proof is quite non-trivial, but I believe some of you might have seen it in a course on algorithms. So my next question is, if we have this kind of a guarantee, if we have one algorithm which minimizes the number of page replacements, why care about other algorithms? Why care about other algorithms such as somebody mentioned LRU? So the issue with this is, well, as soon as you have a cache miss, you need to decide which page you want to replace at that point without knowing what is going to come in the future, right? So that is what makes this FIF completely useless in practice. Okay? So that is the good reason why you should care about other algorithms than FIF. But then, what is so special about LRU? I mean, I could consider tons of such algorithms which only use the past and don't use the future. What is so special about LRU? There is a reason LRU is included in your operating systems book, right? I see. So that is called something locality of something, right? I have forgotten the term. Locality of reference. Okay, good. Yeah. Well, that might be a practical reason, but here is one very practical problem in which that reason does not hold. Let's say I'm trying to multiply a big matrix by a vector. Right? So if you do it row by row, what are you going to need, right? You'll need the rows one by one from top to bottom. And in the vector, you'll need the entries from top to bottom in a round robin fashion, right? So let's just assume that the vector is just larger than what can fit into your cache memory. What is going to happen, right? Right? So the most recently used page will not be needed for the furthest in the future, in fact, right? So this is kind of paradoxical, right? So here is an instance where where replacing the least recently used page does not make sense. Okay, so why LRU? Yeah. Well, there could be several other algorithms which are simple to implement. Let's just say I pick one page at random and throw it away. That's simple. Okay, so this is something probably I should not expect you to know. Well, the deal is LRU has the following nice guarantee, and this was proved in sometime before I was born by two pioneers in this field with the name Slater and Tarjan. So they proved that you give any input sequence to LRU. LRU is going to give you the following guarantee. The number of page replacements performed by LRU is going to be at most k times the number of page replacements which your farthest in future algorithm or the optimal algorithm is going to perform. Okay? This is for every possible input. No assumption about locality of reference whatsoever. Okay? So, such an algorithm is called something called a k-competitive algorithm. Okay? So, it gives a guarantee that the cost of the algorithm is at most going to be k times the optimum possible cost of optimum possible cost of serving the request sequence. Okay? So, this is good, and well, LRU is not the only algorithm which achieves this. First in, first out, flush when full, first in, first out, as the name suggests, the page which comes earlier gets thrown out earlier. Flush when full, as soon as you find that your cache is full and you have a miss, just throw everything away and bring that required page. That is flush in full. All these also have the same guarantee as above. All these also guarantee you that the number of misses is going to be at most k times the optimum possible number of misses. So, more generally, the reason I gave you this example was to introduce you to a field of research called online computation. So, what is online computation? Well, the setup is the following: your input is divided into pieces. Okay? So, there is one online algorithm sitting there. It gets the first piece of input. In response, it has to produce the first piece of output. Then it gets the next piece. In response, it has to produce the next piece of output. Okay? And so on. So, now when it gets I3, it does not have the opportunity to travel back in time and say, oh, maybe I should have output O1 prime instead of O1. That is not possible. Okay? Once it outputs something, that's a commitment. It cannot be changed. Okay? So, I hope you can understand that due to this restriction of your current output being only a function of your past inputs, due to this restriction, I hope you can imagine that in general, an online algorithm will not be able to produce an optimum solution. An optimum solution is going to be produced by some algorithm which has access to the entire input in advance, and then it can produce the entire solution in one go. Yeah, I hope you believe this now. Okay, and in that context, so this setup was kind of defined by Slater and Tarjan, and in that context they defined the notion of competitive ratio. So, since I am going to use that term for many times, let me just quickly, okay, there are chalks here. So, let me just quickly write it. Competitive ratio is going to be the worst case ratio of online algorithms cost to the optimum cost. Right. So, in the context of caching or paging problem, the inputs are the requests given to you, and you can think of the output as the set of pages in your cache in response to every request. Okay. Oh, one thing I forgot to tell you is you should feel free to interrupt me, ask many questions. Okay. So, now let us ask the following question. Well, LRU was a k competitive algorithm. Okay. It had a guarantee that the LRU's cost is going to be at most k times the optimum cost. It would be nice if we can have a k by 2 competitive algorithm, maybe a log k competitive algorithm, or maybe a 100 competitive algorithm, something which is independent of k. Okay. The question is that even possible? Any guess? Maybe just guess the answer, yes or no. I will not ask you for a proof. How many of you would vote for a yes? That is possible. Okay, there is one person voting for a yes. How many of you would vote for a no? There are more people voting for a no. Okay, yes, so your intuition is going in the right direction. In fact, you can prove that you can always come up with an input which forces LRU to have this k factor loss in the cost. Here is how, right? So, think of suppose that you have some algorithm, right? It need not be LRU, it could be anything. Okay? Some algorithm which you would like to claim that it's better than LRU in terms of the competitive ratio, right? So, we'll work as an adversary, okay, and give it appropriate input so that it performs poorly, whereas the optimum cost of serving that input is small. How do we do that? So let's say the initially, let's say, for example, let's just say k equal to 3 for now. And initially the algorithm has pages 0, 1, 2 in its cache. You obviously would like to give some page which is not in the cache, right? Doesn't make sense to request a page which is already in the cache. Okay, so let's say you request 3, and in the response the algorithm says, okay, well, I have replaced page 0 by page 3. What would you do now? What should you request? 0. Okay, some people are saying 0. Yes, why 0? Why not 4? Yeah, so the intuition is correct. Yes, you should request 0. You should request. So the idea is the following: you just take one more page than what can fit into the cache, and every time you just request that one page which is not in the cache. Okay. So why would you not pick 4? The reason you would not pick 4 is even the adversary would have to pay for getting the 4 into the cache. Whereas if you give a 0, the adversary can perform the first page replacement so that 0 still remains in the cache. Make sense? Okay. So let's say the algorithm throws away 1 now. What do you request? 1. Yes. Yeah. So this is the worst you could possibly behave, and so on. Right. So this is the strategy. So why does this work? Let's see that. Well, by design, the online algorithm incurs a miss on every request because we have made sure that the page which we request is not in the algorithm's cache, right? But what about farthest in future, right? So if you look at farthest in future, right? So you are just working with k plus 1 pages. You have just requested one page. Let's say the farthest in future also had a miss. Suppose. Now the farthest in future algorithm is going to throw away a page which will not be needed for the next k minus 1 request at least, right? Look at the next k minus 1 requests, right? Those will consist of at most k minus 1 pages. You are still left with one page in your cache, at least, okay? Throw any such page, that's fine. So what does this guarantee? This guarantees that following every miss, the FIF experiences at least k minus 1 hits. Adversary is all powerful. Adversary can do whatever it feels like.
Can it also calibrate the sequence based on the choice of the algorithm?
That's exactly what it did. That's exactly what it did, right? So it looked at what the algorithm has in its cache and then it decided what is the next input. Okay. So farthest in future, what is the property of farthest in future? Following every miss, you have at least k minus 1 hits. Right? So if you look at, so what is happening? On an average, at most once every k request, the FIF is going to do a page replacement. At most once every k requests. Whereas the algorithm, whatever algorithm you started out with, it is making a page replacement for every request. Okay? So what does this imply? So this implies that no online algorithm is better than k competitive. So, okay. Can somebody share? Watch with me. I've lost track of time. Unfortunately, the time doesn't show up if I do a full, yeah. Sorry? No, can I have your mobile phone with me if you don't mind? Thank you. 9:29, okay, fine. We started a bit late, right? So that should be okay. Oh, wow, okay, I didn't notice it. But we started a bit late, right, Varsha? Yes. Awesome. Okay, good. Right, so this as written is not a complete statement, right? It has a little flaw there. Okay, we implicitly made an assumption, but we have not stated it over here. We assumed that the algorithm that you are trying to defeat is a deterministic algorithm. What is a deterministic algorithm? In particular, I want to stress that it is not using any random choices. It's not tossing coins, right? So given a request, the set of pages it will have in its cache after serving the request is like completely well defined. There is no randomness there, which is why the adversary could run the strategy that we saw. Okay. So in this sense, LRU is optimal. If you want to insist on a deterministic algorithm for paging or caching or whatever, LRU is optimum. That's why you would want to use LRU. Okay, even on worst case inputs, even on inputs without any kind of locality of reference. Okay. So now suppose I enable the algorithm to toss coins. Okay, let's allow the algorithm to use randomization. What happens, right? So as before, let's say the algorithm starts out with 0, 1, 2 in its cache, and you give it a request 3. The algorithm could do the following trick. Okay, it could say that I am going to replace 0 with probability 1/3, 1 with probability 1/3, 2 with probability 1/3, and I will not tell you what I am replacing, right? So the adversary, although the adversary knows the behavior of the algorithm, the adversary does not have access to the coins tossed by the algorithm or the outcomes of the coins tossed by the algorithm, which is why the adversary cannot predict now what exactly does the algorithm have in its cache. Okay, so now what is going to happen? If the adversary gives a request to any page other than 0, 1, 2, 3, it will also have to pay for it. If the adversary gives a request to any of these 4 pages, well, 3 doesn't make sense, 3 is already in the algorithm's cache. So if it gives a request to 0, 1 or 2, the algorithm will have to pay only with a probability 1/3. Okay, so that's an improvement. Yeah, so now the adversary doesn't have a clue what to request next. So this idea is used in something called the randomized marking algorithm. Have you heard of this algorithm, randomized marking algorithm? I think it must be appearing in your operating systems textbooks. Never heard of it? Sorry? Oh, not heard of it. Okay, fine, you'll see it now. So what does the randomized marking algorithm do? Well, it maintains the following information. For every page in the cache, it will maintain 1 bit. Okay, it will keep track of whether every page is marked or unmarked, bit is 0 or 1. Okay, so here I have shown a marked page with a tick mark. Okay. Now, if you give it a request which is to a page which is not in the cache, what does it do? Well, the idea, okay, so the intuitive idea behind this marking is the following. If a page is marked, it really means that it was requested recently in the past. Right? So that is taking inspiration, intuition from the LRU policy. Okay. So the idea on a cache miss, the idea is to replace a uniformly random page which is not marked. Okay, not marked means it was not requested in a decent amount of in the recent past. But here all pages are marked. So what do you do? Well, if all pages are marked, you just unmark everything. Okay, so now you have 3 pages to possibly replace. Right? So now you replace one of them uniformly at random with probability 1/3 each. And once you get in the requested page into your cache, you just mark it. Right? So that has been recently requested, right? So it makes sense to mark it. Okay. So now let's say you get another request 2. So in the first 2 scenarios, 2 is already in the cache. What do? Well, you don't have to replace anything. You just mark the request. In the third case, 2 is not in the cache. What do? Well, you have 2 unmarked pages, right? Replace one of them at random, uniformly at random. Okay. So with half probability each, you have the 2 possibilities. Right? So this is taking intuition. This is using randomness. It is also using the history in some sense. Right? So with the use of randomness and with the use of history, this performs better than LRU. How much better? Right? So it was proved in the 90s that this randomized marking algorithm has a competitive ratio of 2 times HK. What is this HK? This is the kth harmonic number, okay, defined as just the summation of the reciprocals of the first k integers, 1 plus half plus 1/3 plus blah, 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 blah up to 1 over k. So asymptotically, I hope all of you know that this behaves roughly like natural logarithm of k. Raise your hand if you are aware of this. Okay, so fine. Okay, so now you know, even if you are not aware. Okay, so this harmonic number behaves roughly like natural log of k. There is some little constant amount of error. Okay, so this is much better than being k competitive, right? You are now having a guarantee that the expected number of, on every input sequence, the expected number of page replacements made by randomized marking algorithm is at most 2 log k times the cost of the optimum algorithm. That's better than having a k factor loss. Okay. So in the same paper, they also proved that no randomized algorithm can be better than HK competitive. So how does one prove this? That's entirely one lecture worth of content. So I'll not mention it over here. Okay. You are encouraged to come to IIT Delhi and take my class. Okay, so fine. And then later, a group of researchers also found an HK competitive algorithm matching with the lower bound. Okay, so it's like a two-factor improvement over the randomized marking algorithm. Okay, so what is the weighted K server now? So right, so this is what we are going to look at. All this time I just spent in building up the background, but that's I think that was I think worth it. You got to know something new. So in the weighted K server problem, the change is the following. Let's just say that your cache memory is really composed of some small number of what should I call it, chunks, okay, where each chunk has some different kind of hardware, let's say, due to which there is a difference between the page replacement time on every chunk. And obviously, the faster chunk is more costly, the slower chunk is cheaper, which is why you would at all want to use this kind of a setup. Right? So you want a right balance in how much money you can spend and how much average page replacement delay you are willing to tolerate. Okay? So this is this is nothing but the weighted K server problem for the purpose of this talk. Okay, so the question is how do we design algorithms for this modification? How do we prove that they have competitive ratios so much? Well, okay, so just think of each location in the cache as a server. Okay, I'm sorry, I cannot define the K server problem, the unweighted K server problem. It will take a huge amount of time, unfortunately, and there is no better name for this setup. So unfortunately, I have to use the weighted K server problem. Okay, so just bear with that. Yeah, so K is the number of slots in your cache. Okay, so the first step is when we are trying to analyze things mathematically, right? So look for interesting cases which are mathematically clean. Okay, so that is like the first step. They need not be practical, but they are at least clean to analyze. Okay, and once you have a good grasp of the difficulty of the problem, then start looking for practical situations. So what is a mathematically clean version of this problem? A mathematically clean version of this problem is the following. Okay, so let's say every cache location has a different page replacement cost. The ith cache location has a page replacement cost of Wi, and let's assume without loss of generality that this is an increasing sequence. W1 is less than W2, less than W3, and so on. No, K is 8. Okay, so K is not the number of distinct page replacement costs. It is the total number of pages that can fit into your cache. Okay, so with this sort of non-uniform cache, what do you do? What kind of algorithm should you design? Any ideas, any intuition? Think of this as W1 is, let's say, 1, W2 is 10, W3 is 100, W4 is 1000. Let's say there's a big gap between the page replacement costs, and maybe suggest some algorithms. Least cost, so then you'll always replace in the first location. No, I don't understand. But then what the adversary could do is have 2 pages in its first 2 locations and request them alternately. You will be forced to replace on the first location every time, right? The adversary is just going to pay a constant amount of cost. You are going to pay for every request, right? So you really need to use the K slots. It's not so easy. Well, that is not even allowed as far as the problem is concerned, right? I mean, you are not allowed to change the program. All you can change is the page replacement algorithm, the algorithm which will decide which page to throw out on a miss. That's all you can change. Okay, right? So you can't ask your user to design a program which is appropriate for the kind of hardware which you are using, right? I don't understand what you are trying to say. It's okay, never mind. But I think if I understand correctly, you are still trying to change the program which you are running in such a way that it does not incur too many misses. That's not what we are trying to do. We are trying to design a page replacement policy. So that's fine. Okay, so there are a couple of hands. Yeah, there is one hand over here. I think we have time, right? We have a lot of time. Cool. Yeah. There is no probability distribution. Okay, you are suggesting a randomized algorithm. Okay, good. Yeah, go on. Okay. Nice. Okay. High cost. Okay. And what else? Are you keeping track? Are you marking things? Are you keeping track of history? Are you using history at all? Is that all, or?
No, the same algorithm that is suggested earlier.
Oh, the randomized marking algorithm, except that you change the probability distribution. Okay. Well, I must admit I have not even thought of this algorithm. I'm not sure. I'll have to check whether this works. Okay. And the reason why I have not, or rather, I don't know the answer to this question will become evident towards the end of the talk. Okay, so the question is, what page replacement algorithm should we use? How about LRU? Suppose let's try something very stupid. Let's just ignore the page replacement costs, just pretend that they are the same and use LRU. Is that going to be good? How good? I mean, yeah, that is what we are trying to quantify. Okay. So LRU still has some guarantee, right? LRU will give you a guarantee that the number of page replacements is at most k times the optimum number of page replacements. Where is the problem? Well, each page replacement could have a different cost. Okay. So we can still use LRU and get some guarantee. Okay. What kind of guarantee? We can easily prove that the competitive ratio of LRU now becomes k times the maximum weight divided by the minimum weight. Right, maximum page replacement time divided by the minimum page replacement time into k. And how can we do that? Well, the proof is quite easy. This is just a sketch. What is the idea? Well, right, in the worst case, let's just consider worst case scenario. Every page replacement of LRU is going to cost you W max. Okay, so the cost of LRU is just going to be, at most, very conservatively, it's going to be W max times the number of page replacements. What about the optimum algorithm? Well, every page replacement made by the optimum algorithm is going to cost it at least W min. That's like another conservative estimate. And now we know that the first term, the number of LRU's page replacements is at most k times the number of ops page replacements. Right? So if we just put together, you'll get the result, right? So you'll get the result that the total cost of LRU is at most k times W max by W min times the optimum cost. Quite a simple proof. But this is not good enough. Why is this not good enough? This is not good enough because the competitive ratio now starts depending on the weights. Okay. So if the weights are such that there is a huge skew between the maximum weight and the minimum weight, or the maximum page replacement delay and the minimum page replacement delay, then this is kind of going to grow unbounded, even for a fixed key. So therefore, the challenge is the following, right? The challenge is to design algorithms whose competitive ratio is independent of the weight. It should depend only on k and nothing else. So right. So this was one of, yeah. So understanding this problem was one of the major contributions of my PhD thesis. Okay, and at the time I started working on this problem, this was the state of the art. Okay, so it was known since 1994 that you cannot have a deterministic algorithm with a competitive ratio which is less than k plus 1 factorial by 2. And this result is quite intuitive, right? I'll tell you, I can give you the intuition of the proof right over here. So if you go back and recall the proof of the k lower bound in case of unweighted paging, what was the issue there? Well, when the algorithm had a page miss, it was not sure which one page it should replace. Which one of the pages in its cache is not going to be needed for the farthest in the future, right? So it had to commit to one of k choices, and then the adversary made it repent for its decision. Right? So it was the hard job was to make one of k decisions without knowing which one of them is going to be most effective. Here it is quite similar, right? So let's say you just have k plus 1, you just request a sequence consisting of k plus 1 pages, right? So now the algorithm, let's say, gets a page which is not in its cache. The algorithm has to make the following choice, right? So because the cache locations are distinct, they are not identical, how many ways are there to place the k out of those k plus 1 pages into those cache locations? Simple combinatorics. What is it? right? So you have k plus 1 distinguished, k plus 1 chairs of having different color, let's say. And you have, you have k plus 1 chairs, k chairs having different color, and you have k plus 1 people. How can you make them sit in those chairs so that every chair is occupied by exactly one person and there is just one person standing? That's exactly k plus 1 factorial, right? So the question really is, what kind of cache configuration should the online algorithm maintain? So it has to choose one out of k plus 1 factorial configurations, right? So that is vaguely the intuition behind this lower bound of k plus 1 factorial by 2. Well, you have to lose that 2 just to make that proof work. I mean, I cannot explain it any further. So this was known. In fact, the same paper also gave an algorithm with a huge competitive ratio, right? It gave an algorithm with like a doubly exponential competitive ratio, but it was a function of k only. So that was the good news. Okay, so that algorithm was super complicated. It had to maintain a huge amount of history, unlike LRU or whatever, right? So completely useless for practical purposes, right? And then, so in 2004, somebody came up with a very practical algorithm, right? But specifically for k equal to 2, but specifically for a cache which can contain only 2 pages. Right? So there is one location which has a small page replacement cost, there is another location which has a large page replacement cost, just 2 locations in the cache. And they gave a randomized memoryless algorithm. So what is a randomized memoryless algorithm? It's exactly what he was trying to suggest, but without keeping track of any history, right? So if you get a request which is not in your cache, well, you have a hard-coded probability distribution on the 2 pages. With some probability P1, you will replace the cheaper location. With the probability 1 minus P1, you will replace the costlier location. This is hard coded into your hardware. There is zero amount of computation to be done to decide which page to replace. Well, you just have to toss a coin, that's all. Okay, so such an algorithm is called a randomized memoryless algorithm. And they proved that this kind of an algorithm, for an appropriate choice of probabilities, it achieves 5 competitiveness. Okay, so that's still better than 13 to the 2 to the 2, right? Okay, so what was their choice of probabilities? Well, it kind of looks bizarre, but there is still some intuition over here, right? So just focus on the numerators. Okay, ignore the denominators, right? So the probability with which you replace the faster cache location is inversely proportional, or rather, the probability with which you replace a cache location is inversely proportional to its weight. As you suggested, exactly. Okay, except 2 things, except there are some constants involved, and you have why do you have the denominator? Well, the probability should add up to 1, right? Okay, it doesn't make sense for the probabilities to add up to something more than 1 or less than 1. So that's why for that normalization purpose, you have the denominator. That's all. You had a question, Akash? Okay. Right, so this was the algorithm which they gave, and this is what caught my attention. So I was curious to understand 2 things. Question number 1, where the hell did they come up with this probability distribution? Why that 3, why that 2? What would be more intuitive? Well, more intuitive would be to have 1 over W1, 1 over W2. Okay, the one which has a more cost, you replace it with a smaller probability. Where do these 2 and 3 come from? The more important question is, well, this is for only k equal to 2. What about a general k? And this is what we got out of our research. So this work was with my advisor, Professor Sundar Vishwanathan. What we proved is the following. So consider the so we defined the sequence alpha k through this quadratic recurrence relation. Okay, and asymptotically alpha k is still doubly exponential, but that's okay. So we could prove the following for every k. And for every sequence of weights, okay, I can give you a randomized memoryless algorithm. What is a randomized memoryless algorithm? Well, it will have a probability associated with each cache location. Whenever there is a miss, you just sample one cache location uniformly, not uniformly, using this probability distribution and replace it. Okay, so this kind of an algorithm, okay, for an appropriate choice of P1 through Pk, achieves competitive ratio of this alpha k, which was defined through the recurrence relation. Okay, and moreover, yeah, so this is what you would expect, right? Every probability Pi is like a constant divided by the corresponding weight, and then there is a denominator so that the Pi is sum up to 1. Okay, More importantly, what is so special about defining this alpha in this specific way? Why did I not say just doubly exponential or something? Well, we could also prove that no algorithm can have a competitive ratio, no randomized memoryless algorithm can have a competitive ratio less than alpha. So this was a very tight guarantee. It was not an asymptotically tight guarantee, it was a absolutely tight guarantee. Okay, so yeah, so that's a very good question. In fact, we started out with not having those constants. We started out with having a constant 1. We analyzed that, we figured out how to analyze such an algorithm in the first place. That itself was non-trivial. And then we said, okay, let's try to analyze every possible randomized memoryless algorithm. And then pick the one best out of them. Right, so we developed that framework to analyze every possible randomized memoryless algorithm and get a bound on its competitive ratio. And then we figured out how to minimize the competitive ratio by choosing an appropriate probability distribution. It turned out to be this. Yeah, so we gave the optimal choice for these constants, yes, in fact. If you use all of them uniformly, basically disregarding the weights. Oh, CKI is 1, yes, so you will still get a finite competitive ratio, but it will be worse than alpha k. No, I don't think so, yeah. Well, I'll have to figure out what would that be. If I just take the ratio, I don't exactly remember what. I'll have to check whether it's still doubly exponential worse. Okay, good. So where were we? Well, we gave a randomized memoryless algorithm with a doubly, well, we didn't improve the doubly exponential competitive ratio, but as compared to the earlier algorithm which did some huge amount of history tracking and so on, our algorithm doesn't need history at all. Just toss a coin, replace a page, that's all. Okay. So following our work after a couple of years, there was a work which improved the deterministic lower bound, right? So if you remember, right, so the deterministic bounds were the k plus 1 factorial lower bound. I gave you an intuition of why that lower bound holds, and there was a doubly exponential upper bound, right? So Bansal et al. Actually gave a doubly exponential lower bound for deterministic algorithms, essentially closing the deterministic problem, right? So if your algorithm is not allowed to use randomization at all, well, you have to settle for a doubly exponential competitive ratio. You have no choice. Okay. But then the following question remained open. What about randomized algorithms? Okay. So if you are not allowed to use randomization, but you are allowed to use memory, well, doubly exponential is the optimum. If you are allowed to use randomization but not memory, we proved that doubly exponential is optimum. What if you are allowed to use both randomization as well as memory? What happens? Right. So this was the follow-up work with my student at IIT Delhi now. Okay. So the first work, my involvement in the first work was as a student. My involvement in the second work was as an advisor. So until recently, we did not know any better upper bound than doubly exponential. Where do we get the doubly exponential upper bound? Well, you have randomization, you have memory, but you choose not to use one of them. Okay, that achieves doubly exponential, and nothing better was known. What about the lower bound? Well, the lower bound came from the very specific case where all the weights are equal, the unweighted problem itself, right, which I mentioned earlier, the natural log of k or hk lower bound. So there was a 3 orders of exponential gap between the exponentiation gap between the upper and the lower bound. So this was a nice juicy problem to work on, right? What is it exactly? Is it like polynomial, singly exponential, doubly exponential, logarithmic, right? It was wide open, okay, for so many years. And this is what we managed to prove, right? So this is with my, as I mentioned earlier, this is with my BTech project student. So we managed to prove that, well, the randomized competitive ratio, even if you use memory, it has to be at least exponential in k, no better, right? So that is like a doubly exponential improvement over the previous lower bound, right? Log k becomes 2 to the k, okay? Right, but that still leaves one level of exponentiation gap between the lower bound and the upper bound, right? So that is still an open problem in case you find it interesting. Okay, so what are open problems? As I just stated, well, close this exponential gap between the randomized lower bound and the randomized upper bound. What else is interesting? Well, we started out with the practical motivation that your cache is composed of some small number of chunks, right? The number of pages in your cache could be huge, but the number of distinct chunks is small, right? You are not going to use a different hardware for every single page, right? So that was just to make the problem mathematically clean. So this is more practical problem. Let's say you just have 2 chunks, but k pages in each chunk. What is the optimum competitive ratio? Try to understand this. That's wide open. Okay, and then understand the trade-off between the 3 parameters, right? Randomness versus complexity. Complexity as in the amount of memory you require versus the competitive ratio. Right? So what is the exact interplay between these 2 things, right? So for until now there has been no work which says that okay, a good algorithm should use at least this much space or something. No such result is known. Okay. So in my opinion, these are the 3 possible avenues for following up on this problem, and we are still stuck with the first one. I'm working with a couple of students on that. I think that's pretty much it. Well, yeah, so I would like to advertise that I have PhD and MSR positions open at IIT Delhi. So MSR is like a mini PhD. It's a, I think Varsha also mentioned it at IIT Bombay, right? So yeah, it's similar, somewhat similar, anywhere between 2 to 3 years. And if you are interested in the kind of work I'm doing, feel free to shoot an email to me. Thanks a lot for your attention, and I would like to invite questions now. But you will have to use randomization in any case, right? Otherwise, you are stuck with doubly exponential.
Yes, yes. So randomization with memory, like updating the weights based on how recently was it used.
Okay, so he's suggesting use randomization, but also use memory in the sense that also associate some kind of recency with a page in your cache, right? Which will recency score, let's say, and try to replace pages which have a small recency score. I'll have to check whether that works, right? So I must admit that I still don't have enough understanding of this problem to be able to come up with an intuitive argument to and answer and say whether your approach will work or not. So this is a notoriously hard problem. So yeah, right. So again, the reason is the same, right? So put arbitrary constants in those places, consider a randomized memoryless algorithm, analyze it, get a bound on its competitive ratio, and now minimize over these constants, minimize the competitive ratio over these constants. You will actually get 3 and 2. Oh, why do you square it? Well, so I would, I don't think I'll be able to answer it right now, but all I can say is if you look at the algorithm, if you try to analyze it, it's really trying to analyze a Markov chain that is happening, right? Because it's a right, memoryless process after all. Right, so it really depends on the return time of that Markov chain in some sense, and that return time kind of becomes behaves doubly exponential as your k goes on increasing. The state space blows up exponentially, the return time becomes doubly exponential. We don't know anything for other metric space. So other metric spaces, yeah. So for other metric spaces, we only know an algorithm for k equal to 2. The weighted 2 server problem. For weighted 3 server onwards, we don't even know any algorithm. Well, they are also defined using a recurrence relation, and I don't remember it now. They are, I mean, yeah, there's some recurrence relation. I'll give you a reference to my paper. If you are interested, feel free to read it. Do they have a hardware overhead? I'm not an expert to answer that. I mean, how much overhead does it really take for you to be able to toss coins? I'm unfortunately not an expert to answer that.